In this video, we're going to talk about the first isomorphism theorem for groups. Now, this theorem is also sometimes called the fundamental theorem of homomorphisms. And when a theorem is called a fundamental theorem, it usually means it's important. So this is one that we definitely want to try to understand and be able to use. I'd like to start by reminding you about a few important facts that we've gathered in our previous videos on normal subgroups and quotient groups. First of all, in our video on normal subgroups, we proved that anytime you have two groups G and K and a homomorphism phi from G to K, then the kernel of that homomorphism is always a normal subgroup of the domain. And secondly, in our previous video on quotient groups, we proved that anytime you have a group G and a subgroup H, multiplication of left cosets in G mod H by the rule that G1H times G2H is G1G2 times H is a well-defined binary operation on the quotient space if and only if H is a normal subgroup of G. The first thing that I'd like to do in this video is to upgrade the first fact that I just showed you into a theorem which says that if G is a group, then a subgroup H of G is a normal subgroup if and only if it's the kernel of a homomorphism phi from G to K for some group K. Remember, our fact from the normal subgroups video has already established that whenever we have a homomorphism like this, the kernel of the homomorphism is a normal subgroup of G. So what we want to do now is prove the reverse implication that if a subgroup H of G is a normal subgroup, then it can be realized as the kernel of some homomorphism from G to another group K. So to prove this statement, let's suppose that H is a normal subgroup of G, and for our group K, let's take the quotient group of G modulo H. Now remember, we worked hard to prove that anytime H is a normal subgroup of G, the quotient space together with multiplication of left cosets as we described before is a group. Well, now for our homomorphism from G to K, consider the map phi, which maps every element of G to the left coset of H by G. First of all, we need to make sure that this really is a homomorphism. So to see that it's a homomorphism, let's suppose that we have two elements, G1 and G2 in G, and let's think about what phi does to the product G1 times G2. By definition, it maps that to G1, G2H in the quotient group, and by the well-definedness of the binary operation in the quotient group, that's G1H times G2H. But that's just phi of G1 times phi of G2, and so we've succeeded in showing that phi is a homomorphism. Next, to see why the kernel of phi is equal to H, first just think about the definition of the kernel of phi. It's the set of all elements G in the domain with the property that phi of G is the identity element in the codomain, which in this case is the identity coset. Well, in this case, remember that phi of G is the coset with representative G. So for phi of G to be the identity coset is precisely the same thing as saying that G is an element of H. So the kernel is the set of all G's in G, which are also elements of H, but that's just H itself. So it verifies our claim that the kernel is H, and it completes the proof of this theorem. Now we come to our main theorem, the first isomorphism theorem. What this theorem says is that if we have any homomorphism phi from a group G to a group K, then the kernel of the homomorphism is a normal subgroup of G, and the quotient group G modulo the kernel of phi is isomorphic to phi of G. Now, let's write H for the kernel of phi. Then from what we've already said, we know that H is a normal subgroup of G. And we also know from a previous video that the image of a homomorphism is always a subgroup of the codomain. So we can focus now on just proving that the quotient group on the left is isomorphic to the group on the right. Well, in order to do that, let's define a map tau from the quotient group G mod H to phi of G by the rule that tau of a left coset GH maps to the point phi of little g. Now, since I'm trying to define this map by using a representative for a left coset, and since the representative for a left coset is not necessarily unique, I need to first of all check that the map is actually well defined so that it doesn't depend on the choice of representative for the coset that I plug in. Well, to see that it's well defined, let's suppose that GH is equal to G prime H. Then that means that G prime is an element of the left coset GH. So G prime is equal to GH for some H and H. Well then, if I think about what tau does to GH, it maps it to phi of G. But now, since H is an element of the kernel of the map phi, I can multiply that phi of G by phi of H for free. And then I can use the fact that phi is a homomorphism to write that as phi of GH. But GH is equal to G prime, so this is just phi of G prime, and phi of G prime is tau of G prime H. So this shows that tau is a well-defined map which doesn't depend on the choice of representatives for the cosets involved. Now what we really want is to show that the map tau is an isomorphism of groups. So next, let's check that it's a homomorphism. Choose two cosets GH and G prime H in the quotient group, And think about what tau does to the product of gh times g prime h. Well, by definition of multiplication in the quotient group, gh times g prime h is gg prime h. And by the definition of the map tau, that's just equal to phi of gg prime. But since phi is a homomorphism, that's equal to phi of g times phi of g prime. And again, by the definition of tau, that's equal to tau of gh times tau of g prime h. This shows that the map tau is a homomorphism of groups. To see why the map tau is injective, let's suppose that gh and g prime h are two cosets which map to the same point under the map tau. Well then, by the definition of tau, that means that phi of g is equal to phi of g prime. And left multiplying both sides of this equation by phi of g inverse, this gives us that the identity element in the group G is equal to phi of g inverse times phi of g prime. Using the fact that phi is a group homomorphism, this is equal to phi of g inverse g prime, and if phi of g inverse g prime is the identity element, then that means that g inverse g prime is an element of the kernel of the map phi. So g inverse g prime is h for some h in h, and of course that means that g prime is gh, and as we've already seen before, that implies that the left coset of h by g prime is the same as the left coset of h by g. So if two cosets map to the same point under the map tau, then they must actually be the same coset, which means that the map tau is an injective map. Finally, to see why the map is surjective, first of all just observe that for any element k in the codomain of the map tau, because the codomain of this map is the image of the map phi, k must be equal to phi of g for some element g in g. Well then, by definition, tau of gh is then equal to phi of g, so k is the image of the coset gh under the map tau. That verifies that this map is surjective. And since we now know that it's a bijective homomorphism, it gives us an isomorphism between the quotient group g mod h and the group phi of g. Since h was the kernel of phi, this proves the first isomorphism theorem. Now let's take a look at a few examples. And for our first example, I'd like to revisit one that we've seen a couple times before. So we mentioned in previous videos that the map phi, from the multiplicative group of 2x2 real matrices with non-zero determinant, to the multiplicative group of non-zero real numbers, defined by phi of a equals the determinant of a, is a homomorphism, and it's easy to see from the definition that the kernel of this homomorphism, which is the set of everything that maps to 1, is just the collection of all 2x2 real invertible matrices with determinant 1. Now that's a group that we called SL2R, and the fact that SL2R is the kernel of this homomorphism right away gives us that it's a normal subgroup of GL2R. Well, now we can say even a little bit more. By the first isomorphism theorem, we now know that the quotient group of GL2R modulo SL2R is isomorphic to the image of this homomorphism. And now it's not difficult to see that for any non-zero real number, you can construct a 2x2 real matrix with that determinant. So this map phi is a surjective homomorphism, and the first isomorphism theorem tells us that GL2R mod SL2R is isomorphic to the multiplicative group of non-zero real numbers. For our second example, let's let G be the dihedral group of order 16, given by the presentation with generators R and S, satisfying the relations that you see here. And let's let K be the direct product of C4 cross C4, taking X as a generator for the first component and Y as a generator for the second component, so that every element of this group can be written as X to the I, Y to the J, where I and J go from 0 to 3. Now let's start with a map phi defined on the generators R and S, which maps R to the element X squared identity in K, and which maps S to the element identity, Y squared. We claim first of all that this map phi extends to a homomorphism from G to K. And remember that in order to show that that's true, since we have this presentation for the domain, we just need to check that every relation in the presentation is satisfied with the generators R and S replaced by phi of R and phi of S in the codomain. So first of all, when I compute phi of R to the 8th power, I get X squared identity to the 8th power. But since X squared identity is an element of order 2 in K, X squared the identity to the 8th is the identity element in K. That verifies the first relation that I need to check. Now for the second relation, think about what happens when you square phi of S. Phi of S is identity, Y squared. And when you square this, you get identity, Y to the 4th, which is the identity element in K. And finally, we want to show that phi of R times phi of S is phi of S times phi of R inverse. So first of all, phi of R times phi of S is X squared identity times identity Y squared. And because K is an abelian group, I can write that as identity Y squared times X squared identity. But now, using the fact that X squared identity is its own inverse in the group K, This is precisely equal to phi of s times phi of r inverse. So now that I've shown that all of the relations in this presentation of D16 are satisfied with r and s replaced by phi of r and phi of s, we can conclude that phi extends to a homomorphism from G to K. Next, since the domain is generated by r and s, it's not difficult to see that the range of the map phi is going to be generated by the images of these elements. And it's also not difficult to see that the group on the right here is a group of order 4 in which every non-identity element has order 2. So of course that means it's isomorphic to the Klein 4 group. And how about the kernel of this map? Well, we claim that the kernel of this map is the subgroup of D16 generated by the element r squared, which is the group of order 4 consisting of the identity r squared r to the 4th and r to the 6th. To check that, we can just check what phi does to all of the elements of the dihedral group of order 16. Every element of this group can be written as r to the I or as s times r to the I for some I from 0 to 7. Now phi of r to the I is phi of r to the I, which is x squared identity to the I, or x to the 2i identity. Now that's going to equal the identity element if and only if the exponent here is 0 modulo 4. And that happens if and only if I is 0 modulo 2. So the only possibilities here are that I is 0, 2, 4, or 6. Now, a similar calculation, phi of s times r to the I is phi of s times phi of r to the I, which you can work out is x to the 2i comma y squared. But now it doesn't matter what I is, the second component here will never be the identity. So none of the elements of this form are in the kernel of this homomorphism. Finally, combining this information with the first isomorphism theorem, we now know that the kernel of the map phi, which is the group generated by r squared, is a normal subgroup of the dihedral group of order 16. And we also know that the quotient group of D16 by this subgroup is isomorphic to the Klein 4 group. For our final example, let's let G be any abelian group and let's consider the map phi from the direct product G cross G to G, defined by the rule that phi of GH is equal to G times H inverse. Well, first of all, I'd like to prove that this map phi is a homomorphism, and as you're going to see, it's crucial in this proof that G is an abelian group. So pick two elements of the direct product, call them G1H1 and G2H2, and think about what phi does to the product of these two elements. By the definition of the binary operation in the direct product, this is just phi of G1G2, H1H2. And by the definition of the map phi, this is G1G2 times H1H2 inverse. Now H1H2 inverse is H2 inverse H1 inverse, and even though I know I'm working in an abelian group here, I still like to be careful when I write this down. But anyway, the assumption that G is an abelian group means that I can rearrange this product in any order that I want. So I can write it as G1H1 inverse times G2H2 inverse, and now I recognize that that's exactly phi of G1H1 times phi of G2H2. So this shows that this map phi is a homomorphism. Next, I want to show that the map is a surjective homomorphism, but this is really pretty easy to do. So pick your favorite element G of the codomain, and think about what the map phi does to the point G, E in the domain. By definition, it maps it to G times the inverse of the identity, but that's just G. So since every point in the codomain is in the range of this map, the map phi is a surjective homomorphism. And how about the kernel of this homomorphism? Well, let's call the kernel of the homomorphism H. So if the ordered pair GH is an element of the kernel, then it means that phi of GH, which is GH inverse, is the identity element. But of course that means that G is equal to H. And all of these implications are reversible, so that tells us that the kernel of this map is precisely the collection of all ordered pairs of the form G, G, where G is an element of G. So the kernel is a diagonal embedding of the group G inside of the direct product G cross G. Well now, by the first isomorphism theorem, since we have a surjective homomorphism, we can conclude in this example that G cross G modulo this diagonal embedding of G into G cross G is isomorphic to the group G. Now this example is a little more abstract than the previous two that I showed you, but it's a good example of how the first isomorphism theorem can very easily give us interesting information about quotient groups. Okay, well that's the end of this video. Thank you for watching. I'll probably post new videos about abstract algebra, and when I do that, I'll link the next one below. But for now, I think I'm going to switch gears and talk about another topic for a while.